This is the video demonstration of the project of Team 48-3 from NIT Trichy for the Texas Instruments Analog Design Contest 2012-2013. Our project is a portable solar-powered mobile charger. The theoretical solar power reception on only land area in India is about 5,000 petawatt-hour per year. On an average, per day, 4 to 7 kilowatts of solar energy is received per square meter, and India has 300 clear sunny days in a year. This equals 1,500 to 2,000 sunshine hours per year. Even if we take the efficiency of the solar panel to be just 10%, this could amount to over 1,000% of the domestic electric demand. However, less than 1% of the total energy demand of our country is met through solar energy. These shocking statistics urged us to come up with an innovative method to harness solar energy. We explored means to charge cell phones using solar power. This is a block diagram of our proposed solution. The microcontroller samples the phone battery, and if the battery needs to be charged, it checks the solar input to see if it's sufficient to be given to the boost converter. The buck boost boosts this input to charge the phone. If the phone is fully charged, the microcontroller instructs the boost to charge the internal battery instead. This internal battery is used to power the microcontroller and the switches. This is the setup of our project. We have used the following TI ICs: BQ25504 RGTT, a 16-pin boost converter with ultra low power and high efficiency and user programmable over and under voltage conditions. TS12A4517 DBV SPST CMOS analog switches with low on-state resistance of 25 ohms and fast switching speed. We have used MSP430G2231, a low power consumption microcontroller with low power supply voltage range of 3.6 to 5 volts. We have used the Launchpad development toolkit to program the microcontroller. Now let us move on to the working. The solar input from a PV panel is 1.5 volts 150 milliamps. We have used two panels in series. The microcontroller samples this input, performs an ADC conversion to check if the input is more than 1.2 volts, as the boost converter cannot function with less than 1.2 volts for our application. Let us consider the first case. We are going to block the solar input. The input is only 0.71 volts. As the boost converter cannot function with such a value, the microcontroller instructs the switch to open so that the boost does not receive an input and the phone does not charge. 2.5 for the switch means the switch is open and the phone is not charging. Now let us consider the second case. The solar input is more than 1.2 volts. The microcontroller senses this input and instructs the switch to close. Here we see that the switch has 0.05 across it. A low for the switch indicates that it is closed. And we see that the cell phone is charging. Now let us move on to testing the circuit. We shall measure the output voltage waveform, and we notice that it is 4.08 volts. Cell phones have become ubiquitous in our lives. With improvement in technology, the amount of power discharged by the phone is increasing, and phones seem to retain charge for fewer and fewer hours. Statistics show that there are a total of 563.73 million mobile subscribers in India. This means that the number of hours spent charging these phones is also proportional. We believe that the contemporary solution that we have come up with will go a long way in protecting our natural resources and making a brighter tomorrow. We would like to thank several people who have been instrumental in helping us work on our project. Firstly, we would like to thank Texas Instrument for giving us this golden opportunity. This has been a truly enriching experience. We learned a lot about the nuances of going about a project, writing a formal report, and presenting our work as a video. We strongly believe that this will lay the foundation for our higher studies and future research. We would like to thank Mr. Sagar Juneja for coordinating the contest and the timely reminders, and Mr. C.P. Ravikumar for the guidelines and the insightful blogs. Next, we would like to thank our project guide, Dr. N. Ammase Goundan, Professor EEE Department, NITT, who has helped us at every stage of the project and is approachable and ever willing to answer all our queries. We would also like to thank Mr. Binu, Research Scholar under Professor N. Ammase Goundan, who helped us in debugging our circuit and overcoming all the practical difficulties we faced. Last but not the least, we would like to thank Ajanta Electronics and Orange Mobiles for helping us solder the SMD devices.